Okay, well, thank you all for coming. I'd like to talk about lossy image compression. And I'd like to start with a statement of the problem. So, in lossy image compression, we have an image that's a rectangular array of pixels, and we'd like to represent that with as few bits as we can, but not so few bits that we have to give up too much quality. So that's the trade-off. And we can think in terms of two extreme points just to get our head around the problem. So at one end of the spectrum, we have perfect fidelity, which is lossless compression. Lossless compression is where we insist that the decoded image is bit for bit identical with the one that we encoded. And if I do that, then I'm going to have to spend more bits. The ideal code length would be the base 2 logarithm of the probability of that whole image using a suitably predictive probability model. And at the other end of this hypothetical spectrum, I have zero rate. That's when I send no bits at all. And there, the decoder has to just guess what the image was. Both of those are kind of extreme points. The lossless case is actually a realistic scenario. The case where I don't send any bits probably isn't, but it's good to think about. So for anybody who's worked in image compression, you've seen this image before. This is the Lenna Image. It was used a lot in the early days of image compression, and then because people started computing their performance numbers on this image, then other people used it to compare against so that they could compare apples to apples, and it sort of got a foothold. So if you flip through the IEEE transactions on image processing, for example, you'll see this image a lot. Here's an example of compression about a factor of 100 to 1 compression using the standard JPEG algorithm. And I'll talk a little bit about JPEG, but I won't go into the details of the standard. But you can get an idea. When we're spending more bits, about 790 kilobytes, I have the original RGB representation. And then if I compress it with a suitably coarse quality factor with JPEG, then I'm down to about 7.2 kilobytes. We know how to measure bit rate. We just see how many bits come out. To measure the quality, it's a little bit trickier. One of the measures that people like to use is called peak-to-peak SNR, or PSNR. And it looks like regular signal-to-noise ratio, where for the numerator, instead of having the signal variance, we have the range squared, so the range of possible values. Traditionally, with an 8-bit pixel representation, you have the luminance scale from 0 to 255, so we have 255 squared in the top, and then the quantization error, or the total coding error in the bottom. So many papers complain about PSNR as not being the greatest measure in the sense that it may not reflect actual subjective quality. And there's been a lot of research in various places over the years to try to come up with automatic measures that better capture or better track the subjective quality assessments, perceptually weighted, mean squared error, and things like that. But PSNR is unambiguous. It's easy to use. It's easy to compute. It's what other people have used, so you can compare your method against other techniques. And it's a pretty reasonable thing to use in certain situations, namely when the overall noise is low, so the quality is high. It's a pretty good measure. And also, it may be meaningful at lower rates when you're comparing techniques that are similar in what they do, that are comparable. So to compress an image, we're going to have to take advantage of certain properties of the image and also of the receiver or the destination or the person looking at the image. So for any kind of compression, we typically want to eliminate the redundancy in the source. That's true for both lossless and lossy compression. We'd also like to exploit the human visual system. For instance, if the human visual system is less sensitive to, say, noise along edges, if we can hide degradations along edges in images, then we'd like to do that. And then, in the trade-off, do a better job in the non-edge regions, for example. Similarly, if we're not very sensitive to spatial resolution in chrominance, then we might like to take the luminance component and encode that with very high accuracy or acuity, and then give up something on the chrominance components. And we know that we can do that, in fact. In general, we'd like to omit the irrelevant information, concentrate on what's important for the task, or again, with respect to the human visual system. And we're always going to have this fundamental trade-off between the quality and the bit rate. By the way, please stop me at any time if you have questions along the way. It's natural to ask what the best we could possibly do is, and if we're willing to make certain mathematical assumptions and adopt certain types of models, then we can answer these questions to some extent. If I insist on a perfectly accurate replica of the original, so if I'm doing lossless compression, then the quantity that limits what I can, how well I can do, the minimum number of bits I need on average to represent a source without loss is the entropy. And that's a basic result in information theory. Claude Shannon showed it back in the 40s. And it's, I have to emphasize, it's an average measure. It's something that you can't beat on average. And you need a probability model, right? So the entropy is a probability of, it's a functional of P of X. So it's not really a function of the physical source, it's a function of your model of the source. So if you have a better model of the source, then you can get a lower entropy. If you try to cheat by coming up with a model that has a really low entropy, well, then you get hit when you compute the cross entropy, or you try to code with respect to that model, then you get hit with a lot of bits. Okay? So that's lossless compression. Now, is there an analog in the lossy case? And in fact, there is. It's a little bit more complicated, and instead of a single point, it's actually a curve. It's called the rate distortion function. And it takes two things to compute the rate distortion function. One, again, you need a probability model of the source, so that's the P of X. But then you also need a distortion measure, and that distortion measure has to satisfy certain conditions in order for you to be able to plug it into this framework. And the quantity itself can be expressed in terms of a hypothetical test channel. So I have some input to this hypothetical test channel. I look at the output, and I consider all such test channels such that my distortion that I get by using that channel doesn't exceed my specified distortion, so the parameter of the point on the curve. And over all of those hypothetical test channels, I take the minimum of, this is the mutual information. You can see this mutual information, if it's more familiar probably if you multiply top and bottom by P of X. So the mutual information between the input and the output of this hypothetical test channel over all possible test channels that achieve the specified distortion is the definition of the rate distortion function. And the important point about that is it's a quantity that you can't do better than. So if somebody tells you, I've got this probability model that I really believe, and I've got this distortion metric that I think is the right one, and oh, by the way, I want to encode at this bit rate with this distortion, but it's not in the right part of the rate distortion curve. So here's, typically you have a rate distortion curve that looks like that. If the source is discrete, then you can losslessly encode it with zero distortion at some finite rate if it's a discrete source. So that's just the entropy. This, if we're using mean squared error, would be the original signal variance. And so the rate distortion function is a curve that looks something like that. And you can never get into this region down here. So if somebody tells you, I'd like to code down there, and you believe the source and you believe the distortion metric, then you can't do it. Okay, so let's talk about actual approaches to compression. Well, one approach to compression we can call semantic compression. And so I tell you, it's the Lenna image. So that's my code. And that's about, if you compress that sentence, it's maybe 30 bits, 40 bits, something like that. And we've represented the whole image, but we've got a varying degree of fidelity depending on what you come up with in your head. And it's not very useful as a coding scheme, and it's not very easy to do. I should say, I mean, if you think about pattern recognition and image understanding, et cetera, in a certain way, then maybe we could imagine image understanding techniques and advanced sort of artificial intelligence analysis of natural scenes as trying to do something like this. But when we say compression, what we really mean is something to which we can apply the PSNR measure, at least that's what I mean. And so we're talking about techniques that try to preserve the intensity array, the image. So one approach is differential predictive encoding. It has its roots in one-dimensional signal processing speech compression. And the idea there is you're going to encode pixel by pixel. You're going to go through the image in maybe a raster order. And for every pixel, you try to predict what that value is. And the rule is you have to predict it based on things that the decoder already knows. So things that the decoder has already predicted. So the decoder has a noisy version of the previous pixels that it's already decoded. The encoder can know what that is. And so it forms its own prediction knowing that the decoder will do the same thing. Then instead of sending that value, it sends the difference between the prediction and the actual value that the encoder knows. Okay? And the advantage of doing that is if you've got a very good prediction, then that difference will be small on average. It's not going to have much information in it, so it'll be easier to encode. You can get away with just sending bits when you really need to. Okay? So that's differential predictive encoding. And the prediction residual, that error signal, is actually, if you have a really good predictor, it's usually an easier thing to encode. It doesn't have correlation. It's probably got a pretty decent probability density function that you can deal with, etc. Another approach is vector quantization. This is of great theoretical interest, and also some actual coders have used this and have done pretty well. The idea here is to divide up the image into blocks, and we'll see that that's a recurring theme in lossy image compression. Then we treat each block as a point in space, as a vector. And to encode, we're going to replace our input vector with its best representative in some finite set called a codebook of vectors. And then that is what you reconstruct at the receiver. And there the goal is to minimize the average squared error with a constraint on the bits you spend on the index for the codebook index. Another technique, or general class of techniques, is transform coding. And here we analyze the image into a set of frequency bands. And we will allocate the available bits we have to those bands that are most important. And we can do this differently from region to region. And here the idea is that we'd like to just allocate the bits to the spectral and spatial regions where they're really needed. This family of techniques includes JPEG, JPEG 2000, or at least the wavelet coding part of JPEG 2000. And it's not my goal here in this talk to go into the details of these standards, but I will cover the principles behind these standards. So it's the most widely used compression technique. It's also used, or parts of these techniques are also used in video compression. It's an old technique. It goes at least back to the early 60s with Wang and Schultheis. And I'm going to talk about transform coding, sort of vanilla block transform coding first, and then we'll talk about some of the generalizations of it. So here is a transform coder. And I'll walk you through the different parts of it. Let's take a look at it for a minute. So we start with the input. And again, these are, you tile the image. And when I say image, you could typically do each color component separately, or you could do the luminance component and chrominance components separately. So let's say you do a decomposition into luminance and chrominance. So you take the luminance, you tile it up into a bunch of blocks, non-overlapping blocks, and you input one block at a time, and you process it, and then you get a block at the output, and then you tile it back together at the receiver with what you get out. So the first thing we do is we apply a transformation to the pixels in that block. So think of this block. It's a two-dimensional block, but think of it as just sort of unroll it into one big long vector. So now you've got a big column vector. So this transformation, think of it as a matrix that you're applying to this big column vector. Okay? And then at the other end, you're going to collapse it back into a two-dimensional block. Oh, so we'll get back to this. The goal of the transformation is to try to make this vector more compressible in an easy way, and we'll talk about that. So now that we've got the transform coefficients, we're going to allocate bits to the different coefficients and tell the quantizers what those bits are. And depending on how we do it, we may or may not have to transmit that information explicitly to the decoder. Now, the actual lossy step in this whole thing is the quantization. That's where we take a real number, a floating point number that comes out of the transform, and convert it to a discrete value so that it can have an index. So if we didn't have the quantization, we'd have a perfect lossless process, but then we wouldn't have any, we wouldn't have a digitization at all. It would still be floating point. So let me ask, can anybody think of why we use scalar quantizers here? I mentioned a minute ago the possibility of vector quantization. We'll get to it, but I'm wondering if people have an intuition already. Yep. Right. Computationally much more attractive to use scalar quantizers. And so another part of that, though, is we'd like to use a simple scheme like scalar quantization because it's computationally much simpler. The question is, can we get away with it? And so another part of, I think, the reason is that the transform actually lets us get away with scalar quantization. We still would gain something by doing vector quantization in terms of performance, in terms of mean squared error. But because of the transformation, we don't gain as much by doing it, and we'll get back to that. Okay, then we've got, after we have these discrete values, after the quantizer, these are quantization indices, then we encode them and transmit them over the channel. And when I say encoding, I mean both the compression and whatever protection against channel errors you might want to do. If you're not transmitting these images but just storing them on a disk, then you probably don't have to worry about that. But the encoding then would still involve the lossless compression that you would do on the index, on the quantization indices. Okay, let's talk about the transform for a minute. So the transform in traditional transform coding is linear. It's typically orthogonal. And the goal here is to compact the energy or the information present in the input vector into as few components as possible. So after transformation, all of the important information should be sort of packed into only a few of those coordinates in the resulting vector. We should observe that if the transform is orthogonal, then it preserves Euclidean norm. And so if we care about mean squared error, let me model that intermediate processing. So across all the quantizers, think of, in the vector domain, think of that as adding this vector eta. And if I care about mean squared error, I can represent that quantization error, by the way, as additive, whether or not it's independent. I can always just define it as being whatever changed in the signal. I'm just thinking that I'm adding that. And the fact that the transformation preserves norm means that if I look at the mean squared error of eta, or the mean squared value of eta, I should say, then that will be the mean squared error for the overall system, because by linearity, I can represent y as being, in terms of the distances or squared values, the sum of x plus eta, right? So the reason I want to do that is because it allows me to simplify the problem a little bit. Now I can say that the overall error for my whole system is equal to the error that I get in the middle. So whatever I do in the quantization of the middle is going to translate directly into the denominator of the PSNR measure. Okay, so we'd like to compact energy. And how do we do that? Well, let's choose the block size. We'll come back to that also in a minute. But for now, let's say we choose the block size. So here's a recipe. It's a famous recipe for coming up with a transformation that packs as much energy as possible into as few components as possible. So you estimate the covariance matrix of these vectors. So you have a bunch of training data, a bunch of examples. You form, for each vector, you form the outer product with itself. We'll subtract off the mean, then form the outer product with itself and take the average. So that will give you an estimate of the covariance matrix. You find the eigenvectors of that covariance matrix and you normalize them, and then you use those as the columns of your transformation. And if you do that, that'll diagonalize the covariance matrix in the sense that after applying this transform, if you then compute the covariance matrix, that would have no off-diagonal elements. It would be 0 off the diagonal, so it'll be uncorrelated. And the other property is that if you were to then take the product of those diagonal elements, so now those diagonal elements are the variances of each coordinate, take the product of those variances, and that'll be minimized for a constant trace. The trace is the sum, and that's the total energy in the signal. So if you constrain the total energy, which will be constrained if this thing is orthogonal, then you minimize the product of those diagonal elements. And that will translate into coding gain. But that is the sense in which this compacts energy. It's in terms of minimizing that product. So doing this is well known. It has different names depending on what field you're in. It's the Carhoon-Loew transform in electrical engineering. It's the Hotelling transform, maybe also in electrical engineering or maybe statistics. And principal components analysis is another name. So how many have heard of at least one of those? Great. So one question is, why then not just always use the Carhoon-Loew transform? Yeah?
I guess computation is cheap enough as well, but the DCT does just about as well without requiring that computation.
Okay. Yeah, I buy that completely. Yep.
So do you send all dimensions, or you don't have to, right? You have low energy.
Right. So if some of them are completely 0, and you know they're always going to be 0, then you'd never send them.
Well, if they were close to 0, you could send them with low distortion.
Yeah, or with high, well, right, about the same distortion as the others. We'll get to that. Yeah. So let me just amplify what you said. The KLT is data dependent, and it's relatively hard to compute. So that's a little bit extra cost, and you have to ask, well, how much performance am I gaining by doing that relative to the DCT, for instance? Also, you have to tell the decoder what it is, right? So you'd have to transmit that as side information. So that would be an extra, that would come at the expense of the bits you have for the data itself. So instead, people have sort of settled on using the discrete cosine transform as a one-size-fits-all transform that does a pretty reasonable job compacting energy for a wide variety of sources, particularly images, positively correlated sources. And you can see that it's just a sampled cosine. It's a discretized cosine with the right frequencies and the right, for each basis vector, and the right normalizing factor to make it orthogonal. So here's a, oh, I should mention what I showed you was the 1D formula, and this is also a 1D transform. It's a matrix that applies to a vector. When you actually apply the DCT in image coding, you do it separately. You first could do the rows, and then you could do the columns. It's a separable transform. That's what it looks like for n equals 4. If you look at the top row, you'll see that that's just taking the average. As you go down, you increase frequency. Here's an 8x8, an 8-point DCT rather. Again, the top row is computing the average of the block, right, the DC value. And as we go down to the bottom, we see that the coefficients alternate. Every other sign is different. So that's the highest frequency basis vector. Right? So let's talk for a minute about choosing the block size. And let's say our goal is just to compact energy, because that's all we've really talked about so far. So one experiment we could do is try to estimate how much energy compaction is going on for each block size, and then choose the best one. So here's an experiment. For several different block sizes, we compute a DCT of that block size we tile the image into that block size and compute the DCT on each one. And then we skim off the highest absolute value K coefficients out of the, in this case, it's a 256 squared image, so it's 65536 total pixels. So out of that, we choose K that are the biggest ones, right? And we do that over the whole retiled transform domain image. Okay, so that's the experimental setup here. And we're going to plot the reconstruction error as a function of the ratio of k over 65536. So that's what the x-axis is. It's a fraction. This is a fraction of coefficients retained, and it maxes out at 1% in this graph. And on the y-axis is the total reconstruction error I get by keeping only those coefficients and setting all of the other ones to 0. Oh, it's a little bit hard to see. Can people see that a little bit? Great. So the one that's probably hardest to see is the n equals 256, and I can just tell you it's over here on the left. The thing to take away here, I think, is that the large block sizes have a lot of energy compaction if we look at keeping very few coefficients, and there's a little bit of crossover as we go farther to the right. But by looking at this graph, we might be tempted to say, well, if we use a really big block size, then we get the best energy compaction. Now, it's a fact that JPEG doesn't use very big blocks. It uses 8 by 8 blocks. So we're going to try to figure out why that might be. Let me first show you the result of reconstructing using 1%. So that was at the right-hand endpoint. That's using 1% of the coefficients when n equals 4, n equals 8, n equals 16, n equals 64, n equals 256. Okay. So we can see that it starts to get interesting at n equals 16 or so. This is n equals 8 and n equals 4 are not useful. So let's say we were back, instead of keeping 1% of the coefficients, I don't think I have the pictures. So 1% of the coefficients is right here where these three curves, there's actually a third curve in there that's hard to see, where these three curves kind of are on the same point in terms of distortion. But if we were back here somewhere, we'd probably see that the n equals 64 and n equals 256 is significantly better. So let's say we were trying to do a very aggressive compression ratio like that. Would we then choose a big block size? What are some of the reasons why we might and might not? So by looking at energy compaction alone, it misses something. So in particular, let's consider what I'm doing here is I'm plotting the log of the average squared value of the magnitude of these coefficients. So in the case of the 4x4, I take every transform domain block and I square the value and I average that across the whole image for every block in the image, and I take the log of that, and that's what I'm displaying a scaled version of that. And I do the same thing for n equals 16. When I get to n equals 256, well, the whole image is 256 squared, so there's only one block, so there's nothing to average, but it's a squared value that I'm showing, the log of the squared value. So the reason I put this up is to indicate that there is some statistical regularity or predictability in the distribution of energy that you get when you have smaller block sizes that you don't quite have when you have n equals 256. So remember this experiment. Let's say we actually want to design a coder where I'm skimming off the top k coefficients and sending those to the decoder. So I send the decoder, 100 numbers or whatever, and the decoder has to reconstruct the image. Well, the decoder knows that it has the biggest numbers, the most important numbers, but it doesn't know where to put them. So I have to tell the decoder where these things go. And to tell them where they go requires some bits. And it'll be easier to tell the decoder where they go if I have more predictability, right? So the way I've described the experiment, I've got, by brute force, I would have to specify the locations of each of these coefficients in this transform domain tiling, right? So there's 65,000 locations there. If I have k coefficients, that would be the base 2 log of 65,000 choose k. Right, so a big number if I just do it by brute force. Anything that I can do to reduce that number would help. And in particular, if there's some statistical regularity here, and if I even go a step further and say, well, you know what, I'm going to use 16 by 16 blocks, and I'm always going to give the same number of bits to coefficients in the same position in the transform domain, then I wouldn't have to transmit any side information at all. And to the extent that this sort of distribution of energy pattern is regular and predictable across images, then that's a win. I could get away with that. In the case of using the whole image as the transform size, well, then I've got very detailed information here. I could not reliably say that, well, this black pixel is black for this image and it's going to continue to be black for some other image, because the other image might have diagonal structure along some different line, and you may have to send that. So is that clear to everyone? There's one more related point. So the point that I already made was we have to tell the receiver what this information we're sending corresponds to, and there's an activity map, or there's some information that has to be sent either implicitly or explicitly for that. There's also the issue of adapting to non-stationarity. So if I take a big transform of the whole image, that averages over everything in the image. There might be some region of the image that has large, low activity regions. There might be other regions of the image that are highly detailed. Maybe I care more about a face in the image, so I want to do a better job on the face. By using a very big transform, it doesn't allow me to get that sort of selectivity across the image. So choosing n equals 8 seems to achieve a good compromise. So JPEG uses that, and other techniques, I guess, could use that also. Okay, let's talk about, once we have the transform coefficients, let's say we've done a good job with our transform. Now what do we do? Yeah?
So is there a formal theory around the sideband communication bandwidth and how that relates to the net entropy of the image in these transform spaces that allows you to find that n equals 8 is some minimum in a total information flow for PSNR?
I think in the very earliest work on transform coding, they did explicit bit allocation where they had a side channel that would transmit those bit allocations, and there's not a well-known formal theory, but in some of the early work they paid attention to that. So maybe in the work by Chen and Pratt in the 70s, they might have. It seems familiar. I mean, I remember encountering this question of how do you quantize and send the bit allocations, or do you send the local variances, and can you predict the variances, because that's where the bit allocations come from, and that sort of thing. As for a formal theory, I don't know. I guess it would have to be, the way I would do it as an engineer is empirically for a given coder, once I decide that this is what the coder is going to be like, let's then see what we get by trading off, giving more side channel versus main channel.
Actually, I tried this before, and if you're playing with 16 by 16 or any other size, blocks are noticeable when you reconstruct the image. And the size is kind of adequate if you want to do this like an integer map, DSP, and that kind of speeds up the math.
Yeah, well, no, I believe that there are a lot of pragmatic reasons why you want to do it. I just wondered if there was a theory that actually cast it as an optimization problem.
Maybe there is. Yeah. If there is, I don't know. But, yeah.
One other question about block size.
Yep.
I know when we're talking, when you deal with printing images, you know, a lot of these issues relate to how big you want to print something.
Yep.
I mean, is this tied to like screen resolution? When we talk about 8 by 8 or whatever.
Well, maybe the issue you brought up about the visibility of the blocks, I guess, yeah, in terms of the solid angle, you know, that it takes up, maybe there's a perceptual reason for why, depending on the presentation size or the overall resolution of the image, you might then care about the block size. So yeah, I think there are lots of trade-offs to be made. I'm going to talk about other ways to get rid of the blocking artifacts, or at least mitigate the blocking artifacts. But I'm glad you brought that up, because blocking artifacts is a huge issue. Oh, I'm skipping here. Okay, so let's talk about the quantizer. So a scalar quantizer takes some real valued input and it produces a discrete set of output values. So for every input that happens to lie in this region, it would always produce this single output value. So it's a discretization discretization function, I should say. There are two varieties that we care about. There's a fixed rate quantizer, which is very simple. Let's say I have a quantizer that maps everything into 8 possible output values. Then I could simply represent each output value by 3 bits, for example. Another flavor of scalar quantizer is a variable rate quantizer. And in that case, I don't really have a tight constraint on the number of output values. I could have modulo practical constraints. I could have, in principle, infinitely many output values. As long as not all of those output values get used with a lot of probability, in particular, as long as the entropy of the output for that input, namely for those transform coefficients, happen to be, if the entropy is finite, if the entropy is small. Okay, so empirically, if we were to plot the signal-to-noise ratio in dB of these quantizers as a function of rate, we would see that they all kind of have a similar characteristic. After a while, they have a slope of 6 dB per bit. But they have a different overall quality factor, which I've denoted as epsilon there. Yeah? Was that a question?
Changes or expands if you consider tapered quantization rather than uniform quantization?
I need to hear that again, sorry.
Tapered quantization versus uniform quantization?
Yeah, okay. So the question is, what if we were to use a different staircase characteristic? Let's see if I can. So here I've kind of shown a uniform quantizer that peaks out. This is called a mid-tread quantizer because it has 0 as a reproduction value. It sort of straddles the midpoint. If instead I were to use, actually that's not uniform, that's a little bit tapered. So this is kind of optimized for something that has more probability in the middle. So if you optimize the quantizer characteristic for a certain number of levels, let's say 8 levels, and you say, I know my input's going to be Laplacian, for instance. That's a decent model for the transform coefficients sometimes. Where should I put my resolution of my quantizer in order to minimize mean squared error for that quantizer? And the idea there is you put more resolution where the input is more likely, and you give up some resolution where the input isn't very likely. And so that's a very important thing to do from the point of view of mean squared error if you have a fixed rate quantizer. When you have an entropy coded quantizer, what happens is instead of constraining, instead of necessarily spending more resolution on the highly probable regions, what's going to happen if you do that is for those regions, not only will your resolution get better, so your error goes down for those regions, but your entropy is going to be more. Because if you finally quantize those high probability regions, you're going to have a greater number of highly probable output values, so your entropy goes up, so you pay a price. So there's this trade-off, and if you try to do the optimization, and to my knowledge, there's 2 kinds of analysis for entropy-coded quantization that you see in the literature. One is purely numerical. Farvardin and others, I guess, Modestino, did some work on that a few years ago, back in the 80s. And then there's sort of asymptotic analysis, analytical treatments. Goblik and Holsinger and Gish and Pierce and others and Bennett did work that showed that asymptotically a uniform quantizer under an entropy constraint is actually optimal for a wide variety of sources and a wide variety of distortion measures. So uniform quantization sounds like a very simple thing to do. It turns out to be surprisingly close to optimal for a broad class of conditions, and so people do it. I want to qualify that by saying, when I say uniform quantizer, I'm talking about the decision regions. The decision regions are uniformly sized. The reproduction value should always be the centroid in order to minimize squared error. And for the innermost regions, for something like a Laplacian source or a gamma source or broad tail density, that may be far from the midpoint of the uniform quantization region. That's a great question. I hope I answered it, and I hope I didn't say too much. Yeah. Okay, so empirically, we could just look at the error we get as a function of rate when we use these quantizers. And in the case of a fixed rate quantizer, I'd have a bunch of discrete points on this curve that I would get. In the case of an entropy coded quantizer, I could change it more continuously by changing the quantization resolution for a fixed input, and then see what the entropy I get out is. And in all cases, I'll see a curve that kind of can be approximated in that manner with that parameter epsilon. And if I just add up all of the contributions from each of those quantizers in my transform coder, I just get the bottom expression, which is the sum, which I show again at the top here. And remember, what I'd like to do in bit allocation is allocate bits to minimize the sum of these quantization errors subject to an overall budget on my number of available bits. So that's minimizing a smooth function with respect to an equality constraint, so I can use Lagrange multipliers. This is my constraint. I say the total number of bits I'm spending can't exceed my budget R. This is my total error. So I form this Lagrangian. Lambda is the Lagrange multiplier, and I take the partial derivatives with respect to a particular R. And if I do that, this is just an exponential. This just picks out the R that we're differentiating with respect to. And I get a constant times the distortion itself again has to equal a constant for all j, for all R sub j. If I wanted to solve for the Rj, I would say that it's proportional to the log of the standard deviation, or the log of the variance. And if in the early work on transform coding, people actually did this explicitly. So they would apply the log variance rule, and then they would have to jump through some hoops to ensure that when we have small variances, which we will have for some of the transform coefficients, right? That's because we're doing compression. And we've compacted away some of that energy, so we'll have a lot of small values. This formula, the optimal formula, would tell us that some of the bits should be negative, and we can't do that, so we have to re-optimize. But we don't do that anymore because there's a better way. And going back to entropy constrained quantization, so if you consider just for a moment the idea of using a uniform quantizer, and we know that from an entropy constrained point of view, that's a pretty reasonable thing to do for a broad variety of sources and distortion measures. We care about squared error, but including other distortion measures. So let's use a uniform quantizer, and let's consider the high rate case. So that's the case where all of these quantizer, so I've got some staircase, and let's say all of the levels are being exercised to some significant extent. I could then approximate my error for any one particular quantization region. The contribution from that region would be approximately uniform between plus and minus delta over 2. And the error associated with that, the squared error, would just be the square of that density uniform between plus and minus delta over 2. So I get delta squared over 12 for that error. So it's only a function of the step size. And when I look at the output entropy, I'm going to get some number of bits. But the error doesn't depend on those number of bits. It only depends on that step size. So that's my parameter. If I set the step size, I set the quantization error, at least asymptotically. So the nice thing about this is if I just use the same step size for all my coefficients, and if we go back and look at this rule that I had, if I set the same step size for all of the coefficients, then I actually implement this. Because what this says is that my quantization error, which is everything but for that quantity, should be constant. And in fact, that quantity will be equal to delta if I use the same delta for all of my coefficients. So that's kind of nice. That's a simplification. And JPEG essentially does this, but it has some provision for multiplying these step sizes differently for different spatial frequencies, and I guess chroma and luminance might be different also. Okay, so let's go back to the transform. Right, so now I've sort of been talking about separable transforms, but now I want to make that restriction explicit. So I'm only going to talk about separable transformation. And I'd like to interpret the block transform in terms of multi-rate signal processing. So the way I'm going to do it is, let's consider an image row. I'm doing separable processing, so I consider the row. And the block transform then lops off blocks of 8, say, and applies a matrix transformation to each block. I get my transform coefficients, and then I invert the transform and reconstruct the row. Another way to think about this is in terms of a convolution. Let's consider this blue convolution kernel. So each line here represents a different weighting. I'm going to take the weighted sum of, in this case, 4 pixels, compute the weighted sum and store it away here. I'm then going to slide over by 4. I'm going to skip over and do the same thing and store it here, etc. Then I do the same thing for a different set of coefficients. I convolve, record the value, slide over. And I'm not showing the other 2 filters that I'd have to use to apply this scheme. I hope you like my artwork. Lossy artwork, yes. I can interpret that in terms of a critically sampled filter bank. So critically sampled just means that I'm subsampling by whatever I have to make sure that I don't increase the number of real values that I see crossing this boundary and crossing this boundary. I preserve the total number of degrees of freedom. I have a set of k filters. I subsample each one, in this case, uniformly by a factor of k. So I throw away all the samples except every kth one. I do some processing. The processing would be quantization in this case. I upsample by inserting k-1 zeros between adjacent samples in my subsampled stream. And I put it through an interpolating filter, and I add everything up. And it's plausible that in the absence of intermediate quantization or any other corruption of these intermediate values, that I could design these filters such that what I end up with is the same as the original. That would certainly be the case if each one of these things were kind of ideal, right? If each of the bands were ideal. So I'll come back to that question about how to do that, but first I want to motivate this whole approach. So now I've got a filter bank instead of a block transform. Let me think in terms of the input spectrum. So we know that the input is correlated. In terms of the power spectrum, correlation and power spectrum are related. The power spectrum is a Fourier transform of the autocorrelation. So we expect an equivalence there. If I look at the spectrum for a 1D signal, and let's say the spectrum is highly non-uniform, it's non-flat. So here's 0 to pi, and here's the mirror image frequency. So if you think of on the unit circle, so this is the z-plane in filtering terms. There's 0 frequency and there's pi. So I have a spectrum that has a lot of energy down here, and it sort of goes down to 0 as I go over to pi. What I'd like to do is allocate bits to where the energy is, where the information is. So I split up the spectrum into these bands. I put more bits on the more important bands. And if I look at what happens to each band after subsampling, well, subsampling, this is after bandpass filtering. I just pick out these 2, say. And then after subsampling, well, that changes, that remaps my unit circle, the Nyquist theorem and all of that. So when I resample, it remaps where pi is. And I see that the resulting spectrum looks a little bit more flat in this example. And you'll see, in general, since these bands are pretty narrow, they have less time, the spectrum has less time to change in that band. So when you stretch it out over the whole spectrum by subsampling, in fact, you expect it to be flatter. And a flat spectrum means uncorrelated. So we've done 2 things. We've compacted the energy by picking out, by separating the spectrum out into these bands. And then we've also decorrelated these sources, because after subsampling, we have less correlation. Okay, I'm going to sort of skip over. Yep.
So one question. This works fine, but how do you know how big each band should be? Because that's different from image.
Yep, great question. So I will come back to that. What about aliasing? Well, there's an existence proof that we could get perfect reconstruction in the absence of intermediate quantization. The existence proof is that we can interpret a block transform in terms of the filter bank. So then the question is, well, is the block transform the best you can do? And we can tweak from there. But this at least shows that you can get away from the aliasing problem, because a DCT implemented as a filter bank gives you perfect reconstruction. Okay, so let's look at the DCT as a filter bank. I could simply take each row in that forward transform matrix and plot its frequency response, treating it as a filter. And if I do that, I see that I get some band separation. So kind of hard to see the different colors, but they're also different line types. These are side lobes down here, but you can sort of make out 8 different bands there. These are the first 2 convolution kernels. And there are two things that we'd like to do here. One is we'd like to get rid of these blocking artifacts. So one way to do that is to allow these kernels to overlap from block to block. And another thing we want to do is maybe give different frequency selectivity to different parts of the spectrum. So when the filter length is greater than k, then we have something called a lapped orthogonal transform. One question is, do we want to try to get these ideally frequency selective filters, or would it be better to use something else? And we notice that when we try to increase the frequency selectivity, we get more ringing, and perceptually ringing is very objectionable. So let's try to optimize these filters while minimizing ringing, and so we can increase the filter length, and we see that when we do that, the side lobes start to go down. And if we look at the time responses, we see that the time responses, when we allow them to grow, they'll ring, but if we optimize in a very careful way, the ringing isn't a problem. And that's for the second frequency band. Yeah?
Conceptually, the first lobe of the ring is my impression is it helps.
Right, right. So I actually, thank you. So sharpened Gaussian filters and Mexican hat filters, et cetera, have exactly one excursion below 0, and then they stop ringing. And my optimization procedure that produced this actually respected that. So good, thank you, good point. The second opportunity for improving compression is to use different bandwidths. And the intuitive reason for this is we want to have short spatial extent filters for edges because we don't want to be smearing what's happening to the edges all over the image. At the same time, if we've got a nice big blank region, we'd like to compress that well by using, say, just one basis function for that whole big blank region. So we'd like to have different sized filters and correspondingly different frequency selectivities. And one way to achieve that is to assemble multiple filter banks in a tree structure. So we recursively divide up the DC axis, the DC region, and we could apply this separately to images. For instance, I do a 2x2 decomposition both vertically and horizontally. Then I repeat on the DC, on the low pass band, and I keep going. I'm going to skip this. Let me actually skip the vector quantization. Okay, so here's a separable decomposition where I use a 3x3 decomposition. Yep.
Gosh, I'd like to see all the slides. Could you make this into 2 lectures?
Yeah, so Dick wants me to come back for another one. I kind of chose the material for this one to, on the basis of what I thought I could get through. But yeah, I'll talk about the VQ again. And in fact, it's probably good to skip it completely rather than to try to cover it.
So we have a scheduling snafu. If anyone's here for life of a query, I'm going to figure out where we're supposed to be, since it doesn't appear to be here. So hang out here, and I'm going to go figure out what's going on, and I'll be back.
Okay, I don't know if that buys us a couple of minutes. I shouldn't go over anyway, but at least I feel...
wait, so you're supposed to be done at 10.
Yeah. Are you here then? Or?
Yes.
Oh, then let me just stop. I'd like to just wrap up in 30 seconds, though. So let me just talk about the top bullets. So we trade off rate and fidelity. The transform actually rearranges the input to make the regularity more exploitable. And by thinking of the transform in terms of a filter bank, we get some good insights that allow us to get rid of the blocking artifacts. Bit allocation and entropy constraint quantization all work together nicely. Thanks a lot.